So ecstasy is obviously a drug, and this is they stamp them with pretty little symbols. It's they're not safe. It's not a safe drug. Let's talk about what some of the side effects are specifically. What does it have to do uh, with osmosis? So as we read this, it says Susan, a new intern at a local hospital, was working on the admissions desk on Monday morning. A man and a woman rushed through the doors carrying a second woman. Help, can you help us? Susan and a nurse rushed them into the exam room. What happened? Susan asked while examining the patient. We don't know, the female student sobbed. Brittany started feeling sick at a party last night. She came home and went to sleep, but then couldn't wake up this morning. She was acting so weird, we decided to bring her here. Susan carefully observed the woman lying on the table. She was rolling her head and clearly seemed confused. However, there were no obvious signs of trauma. Has Brittany taken any drugs recently? Susan asked, and the two students hesitated and looked at each other. Finally, one of them nodded. I think she took some ecstasy last night. Okay. Kind of a typical emergency room visit, I would think. Susan thought for a moment ecstasy had been fairly popular on the party scene several years now. She had seen some people on the drug become somewhat confused, but not delirious. Maybe Brittany was having an adverse reaction to the drug. It was a start. To be safe, Susan ordered a series of blood tests. In the meantime, she checked her medical references to find out as much as she could about how ecstasy affected the body. Which one would think? So, there's some emergency room mentions about ecstasy, which is also known as MDMA. And you see in 1999, which seems like a long time ago, but I'm sure this drug is still a problem. I don't know if it's as big a problem. There were almost 3,000 mentions in emergency room departments in 1999, almost double, more than double in 1998. So it was really, in 99, it was a real big problem. And here you can click on this and you'll see the molecular mechanisms by which ecstasy works. To summarize what the ecstasy pathway that was discussed in the mouse. Now, if you chose the wrong mouse, you might have seen the meth mouse or the some other drug interaction. Each mouse in that lab experiment online looks at a different pathway and how different drugs impact the mood of the mouse and the addiction that the mouse experiences. Now, the particular pathway that was looked at with ecstasy was a protein receptor on the cell surface of a neuron that normally interacts with a molecule known as serotonin. And as a neurotransmitter allows for a signal, a molecule kept in vesicles inside one cell, to be released from the vesicles out through a concentration gradient inside the the synaptic gap, into the synaptic gap from one cell to the other through these transporters. The neurotransmitter is released into the synaptic gap. The neurotransmitter then binds to the second cell, which sends a signal. This cell could induce a pleasurable effect. It could induce a number of things. It depends on the two cells that are involved. So if the cells involved have to do with pleasure, then that is the effect that's elicited when the molecule binds. The body is not meant to feel pleasure all the time. There are ramifications to having this kind of neural interaction occurring. One of the problems is what you see with a lot of drugs, which is addiction. It's only one of the many problems. Here you see the serotonin. Normally, ecstasy then takes the place of serotonin, and in fact is taken up by the cell faster than serotonin would be, and the pathway for ecstasy is as a mimic. So instead of it looks like mimic, meaning it looks like or mimics the molecule serotonin, it enters the cell instead of serotonin, and then you have these mimics inside the cell that was sending the signal, the axon, sending more serotonin or keeping the serotonin in the synaptic gap. This is known as a synaptic gap. That's where the signal's sent. And so the serotonin stays in synaptic gap longer. It binds to the receptors. That binding to the receptor causes the effect. Again, what is that effect? It depends on the cells, the pathway. The things that are affected by this particular drug with these particular receptors, in general, are mood, sleep, perception, and appetite. So all these are impacted. Now you should really pay attention to this one, which is perception. Perception is how we interact with the world. And if this is impacted, then reality tends to be warped. And that's an issue, right? So you really can't, while you're on this drug, the world seems different from how you perceive it normally, which for some people crave this perception change. The problem is that you're not perceiving it the way the rest of us do, and that could lead to all kinds of issues. Sleep obviously is necessary for a healthy brain. You're impacting sleep, you're impacting the health of your brain in general, and of course your mood. It's not necessarily that your mood is better. It can be, especially when you're off the drug or on the drug or the various concentrations of the drug, but the mood, sleep, perception, and appetite are all impacted. You could start losing weight or gaining weight. There's all kinds of different interactions that could be happening here. Indirectly, though, you do have a slight increase in the dopamine concentration, the dopamine pathway. Remember, dopamine is involved in the pleasure pathway, so it slightly increases the sense of pleasure, but also is, because of that, is slightly addictive. So you have to really be careful with how drugs interact. You see, it's not just one-to-one. It's not just one drug does one thing. The drug can do different things depending on the pathway it's impacting, and often does different and, if not opposite, effects on different individuals. With drugs like these that interact with neurotransmitters, a lot of this is very individualized. So be very careful with these kinds of with how you perceive how these drugs work, because obviously they don't work as simply as some people would have you believe. MDMA, or ecstasy, is a methyl deoxyribonucleic methamphetamine. So it is a meth. You might know, a lot of people call it meth. Now, meth itself is slightly different. And you saw the pathway if you go back, if you want to, you can go back and look at the pathway. That particular mouse in the interactive site. But MDMA is a synthetic psychoactive drug chemically similar to the stimulant methamphetamine, so it's very, very similar to meth, and the hallucinogen mescaline. MDMA acts as both a stimulant and a psychedelic, so it actually impacts how you perceive the world. It produces an energizing effect, distorts both physical and cognitive sensations. So it's not just how you sense the world physically, hot, cold, rough, smooth, light, dark, but it also impacts your thinking and may impair your memory. So you may not even remember half the things that occur while you're on this drug. MDMA affects a neuron's ability to use the chemical serotonin, which we just looked at. Serotonin plays an important role in regulating mood, aggression, sexual activity, sleep, and sensitivity to pain. Research in animals indicates that MDMA is a neurotoxin, meaning it kills your nerve cells, and MDMA is potentially harmful to the health and on rare occasions may be lethal. All right, so let's go on and take a look at the rest of this. MDMA may affect your blood pressure, pulse rate, body temperature. It might make you hypothermic. It might make you hypothermic. It might make you sweat and have a fever-like symptoms, or it might make you your temperature drop too low. Your temperature can go too high or too low. Hypo. Water balance, you can get dehydrated, or you can take in too much water. Blood sugar level can go up or down, and vision is impacted. So all these are possible impacts of this one drug. Again, depending on the concentration and on the individual taking the drug. Brittany's test results show that her heart rate is 60 to 100, normal's 90, so her heart rate seems normal. Blood pressure is 90, anywhere from 90 over 50 to 140 over 90. This would be on the lower end, this on the higher end. She was 135 to over 87 on the higher end. Temperature 98 to 100, and Brittany's was 100, so slightly elevated, but nothing. Her temperature slightly elevated, her heart rate, her blood pressure slightly elevated, but nothing that one would be, that would need treatment for in the moment. Glucose should be between 60 and 109 and 72, so it's normal. Sodium is 135 to 146, again in the blood, in the solution of the blood, in the solvent, right? It should be 135 to 146. Hers was 115, so slightly low. So, seeing as we're talking about osmosis, I think it's important to make sure we understand that when we're looking at the cells, the outside the cell, and I hate drawing it this way because I want to remind you that blood vessels themselves are made of cells. So it's not like the blood cells are the only cells impacted. It's the cells that are surrounding the blood as well are impacted by the movement of water. So sodium is, in Brittany, is 115, which is lower than normal. Low sodium. It's low. How significant is that? We'll find out. Potassium should be at 3.5 to 5.5. It's 2.9. So potassium is low. Notice how I'm drawing these things out. And I'm identifying what I believe to be not to be pertinent and not within a normal range. How do I know it's not within normal range? They tell me what normal is. Chloride ion, it's 95 to 109, and that's low. So So these ions seem to be low in the blood, and that's kind of a caution to me right at this point. Oxygen should be between 80 and 100. This is 93, so it's normal. CO2 should be 22 to 32. 24 is what Brittany has, and it's normal. So it seems that the only abnormalities in Brittany's blood are the salt concentration in the blood or outside the cells. What do the test results suggest causing Brittany's illness? High blood pressure, rapid heart rate? Well, that's not an answer because that was not normal. That was well within normal, or at least within normal. Hypoglycemic? No, her blood sugars were low, normal. Hypothermia? No, her temperature was relatively normal. You know, it was higher than the stated temperature, but not by much. And temperature can range. So when they put 98.5, some people might be 96, some people might be 100. I would be worried with temperature if it was 103, 104, but, maybe it might be an answer here. This might be something to be considering if I were doing this as a student in class. I might have a question about that one, since technically, according to the chart, it was outside of normal. Hypothermia, no, because it was high, if anything. Excess water, too much water, or dehydration. Now, what would you expect if there's a cell and there's a hypertonic solution, increase ion concentration? Which ions were tested? Chloride, potassium, and sodium were all tested, and you saw it on the chart. If the ion concentration were low, then what you'd expect is water to go into the cells, right? As the cells swell up. The cells themselves swell up, not the tissues, not the blood vessels, so the blood pressure wouldn't go up necessarily, but as the water would flow into the cell because it would go into the higher concentration. Normally it's isotonic, and since the ion concentration is lower than normal, these three were all low, then I would expect, and I don't know what the answer is yet, but this is what I'm thinking, is that the water would be going into the cells, so there'd be causing too much water to go into the cell, so excess water I would think would be the problem here, and of course dehydration would be the opposite. So that's what I would be thinking, just simply with the knowledge that I have on osmosis. If my salt concentration in the blood was low, I would be thinking then the water would go into the cells, into all the cells, into the tissues, and the cells would swell up. The cells would swell up, not the not the spaces around the cells. So you have excess water, and why would your salt concentration be low? Well, one of the symptoms of taking ecstasy, one of the effects, if you remember, is possibly taking in too much water into your blood. If you have into your body, and if you have a certain set of concentration of salt, of sodium, of potassium, and of chloride, all in a certain amount, a certain volume of liquid, like blood. You have a specific volume of blood, of water, which is a solvent in blood. You have a specific concentration of them. The number of these don't change. What happens when we add more water? Because we're taking in ecstasy, we're impacting our senses. We drink more water, extensive amount of water. What happens to your salt concentration? Well, your salt concentration then becomes less. And if that happens, then water is going to go into the cells. So drinking excessive amounts of water could be impacting the concentration of ions in the blood, which would then allow force water through osmosis to go into the cells. That swelling of the cells could impact their function. But that's what I'm thinking. I haven't read anything that says that specifically. This is the path. This is the logic that I'm using, and we'll see if I'm right. So here we have concentration amount of one substance solute is dissolved in a given volume of another substance solvent. So again, without any further information, I'm thinking this is very similar to the blood. And then here in side B, you see that there's less. So maybe this is a cell, or maybe this is the cell. Side A is the cell, and side B is the blood. You added water, so the relative percentage of water to salts changed. It's less on this side. So this side would be hypotonic. This side would be hypertonic, right? Hypotonic. So one would expect water to move in this direction, try to reach equilibrium. Once that happens, this side would swell up. Well, let's see if that's what they're going for. Susan spoke to students waiting in the area. Did Brittany have much to drink last night? Just one beer, replied one. She had a test today and wanted to study. She did drink a lot of water. Now, there it is. Now I'm feeling confident that my thinking was correct. She drank a lot of water. Again, reducing the ion concentration by increasing the solvent, right? Remember what we discussed in class, that there's a whole, there's a pie. You're dealing with 100%. If you increase the concentration of water, you're decreasing the concentration of salt. All right, a solute. Increase the solvent percentage, you're decreasing the solute percentage. So she drank a lot of water. So you're supposed to do that to prevent hangover, aren't you? She seemed really thirsty. Now, why would she seem thirsty? And so that would be a question someone might have in your mind. Why would she be thirsty? Well, remember, what did we say? Ecstasy, a methamphetamine-like drug. Well, it is a methamphetamine, but a meth-like drug impacts your perception. And the thirst comes from the impact of the drug, of the interaction of this serotonin mimic setting off a pathway in your brain that lets you think you're thirsty. It sends a signal that says, I am thirsty. You are thirsty, but you're not really thirsty in the natural sense that you're reacting to some environmental need for water, but you're reacting to the drug's impact on the neural pathway that stimulates the feeling of thirst. Susan thought for a minute. Normally, Brittany's kidneys would respond to drinking a lot of water to produce large amounts of dilute urine. However, ecstasy acts as an antidiuretic. Now, there is another issue. She's drinking a lot of water because ecstasy is making her drink a lot of water. Makes her think she is thirsty when she really doesn't need to. It acts as an antidiuretic, which means she can't get rid of the extra water. So her urine was concentrated. Right? So now instead of having that pale yellow in the toilet, it's that auburn yellow, that dark yellow. Now, I keep talking about how important poop and urine is, and how important it is that you look at what's coming out of your body to have to constantly monitor your own health. What is normal for you? You should always be aware of what's going on inside your body. And one of the ways we can tell what's going on inside your body is to see what's getting in and what's not getting in, your poop, and also what's coming out, which is your urine. Now, also, if you're bleeding, you have blood in your poop, then there's stuff coming out in your poop that shouldn't be. That's also a concern. So monitor these two bodily functions in order to make sure that you can be aware of your own need for medical attention. So this would prevent Brittany's body from getting rid of excess water. It could cause her electrolytes to fall. So she was taking in a lot of water. There was a lot of water going in to Brittany. And there was not a lot of water going out. So what the impact of that is that her chlorine, her potassium, and her sodium ions were low. They became low. Now that's electrolyte concentration, which then, what did that do? That forced osmosis that initiated osmosis to do its thing, and water started moving into the cells, causing the cells to swell. All right. Now, could this be causing your symptoms? My guess would be yes, since it would be kind of sad to go through all this, and then the answer would be no. I have an idea in my mind why the symptoms would be occurring, but let's let the case study speak. All right, let's move on. So this osmosis animation in this case study, it lets you walk through what osmosis is, right? I think we've done enough of that we can move on. But if you need to, and I would suggest it strongly to go to pbslearning.org resource and go look at osmosis. Assume movement of a molecule is limited. It can move to the opposite side of the container or stay where it is. If movement is random, what is the probability 0 to 100% the molecule will move to the opposite side? Well, it's 100% eventually if it's random and it can move the opposite side of the container or stay where it is. The movement is random. What's the probability 0 to 100% it'll move to the opposite side? Eventually, over time, 100% it'll go from to B, and then later it'll end up in A, and it's random movement, right? What would stop it from getting to B? It might take it a while, but certainly it's going to move, right? So it's 100%, I would hope you agree. Assume there are 10 molecules on one side of the container. How many would you expect to move to the opposites? Well, this is kind of a tough question because of the way they phrased it. But what I would expect to see is that the molecules would keep moving. There'd be eventually 5 on this side and 5 on this side. Now, that's not where it's going to stay because the ones on this side will move to the opposite side, and then these will also move in that direction. What is going to determine that is how many are on this side versus this side. So initially, there's going to be a large movement and net movement in this direction towards the right initially. So initially, I would expect there to be, a large movement to the right, and only a few move. And once you get a couple on the right-hand side, only a couple move in the opposite direction. And eventually, though, over time, there would be 5 and 5, and what I would expect is ultimately there to be a dynamic equilibrium, a movement of molecules in both directions, as you see the double-headed arrow, in an equal rate, because the concentrations are equal. The only other impact would be how permeable this is, how much space, how much surface area there is for it to move, and then the next thing is what is the temperature of the solution. Since the temperature of the solution will be the same, the surface area will be the same, the concentration is the same, the movement in both directions, therefore, would be the same, and you'd have an equilibrium reached. The number of on the right and left at any given time, on average, is going to be the same. So diffusion with many particles, you could take a look at this and play around with those. That particular activity there. Which statement best describes how these molecules will behave over time due to random movement? So what you'd expect, as we said, I hope you understand, that assuming there's random movement, the red molecules can move, the red molecules will move from left to right until they're both equal. And then they'll keep moving in both directions. So will the blue ones. They'll be moving in both directions until both are equal, and they'll just keep moving back and forth at a constant rate after that, keeping the concentration the same. So it will eventually move towards an isotonic condition. Red molecules move from A side to B side. Well, that's for sure. That's going to happen. Blue molecules move from B side to A side. Okay. All the molecules will move so that red and blue will become equal on both sides. More molecules will move from A to B than from B to A. So what you'll get is ultimately all the molecules are going to move to red and blue until both sides are equal, right? And so they'll find an equilibrium. The red will move. Usually, red is going to move faster because it's a higher concentration of red on this side. They'll move faster, and they'll get to a point where they're equal on both sides. Brittany's inside of her cells were 300 millimoles of salt. Outside cells is 250 millimoles of salt, millimolar of salt. Well, before we even go on, what would you expect to see? Knowing that, unlike the previous examples, salt does not pass through the membrane easily, the sodium, the chloride, the potassium. So what would you expect to happen is that water is going to go towards the hypertonic side, so water is going to go into the cell. Which of the following molecules could move through a phospholipid membrane with the least difficulty? Well, it's not going to be glucose. It's not sodium. It's not an amino acid. But oxygen does. And that's going to be the least difficulty, because it says least difficulty. The answer is going to be oxygen. But of course, water is the one we're really interested in. The second least, anyway. How do molecules cross the membrane? Hydrophobic molecules cross easily. Hydrophilic molecules get repelled. Water crosses, no problem. We said this repeatedly. I think it keeps coming back. I hope that's important enough in your mind that you see that it needs to be, it should be clear that that's the point here. Aquaporins are interesting molecules. They're channels. They're channels that are membrane-spanning proteins that allow water to move easily. They help water move through the membrane. They are a method of facilitated diffusion. So water's going from inside and outside. No water normally does this. It's not, the aquaporins aren't absolutely necessary, but it increases the rate of osmosis since it's rather comparatively slow without aquaporins. And the cell wants water regulated. It's obviously essential to cell function. So aquaporins are created by the cell, produced by the cell, and then embedded in the membrane. So when we look at inside her cell, Brittany had more ions, whether chlorine or it looks like these are are positive ions, right? Are more why? How do I know they're positive? Because if this little Mickey Mouse looking molecule, these two are hydrogen, that's oxygen. This is partially negative. It's being attracted to a positive object, where the sodium potassium chloride's negative, so it wouldn't be attracted to it that way. The opposite side would be attracted to it. And regardless, there's more of these ions in here. There's less of them out here. These ions cannot move easily, so water will flow through the aquaporin, and it will flow in this direction to allow the solute to be a less percentage, for there to be a decrease in the concentration, so that the concentration on both sides can be more equal as they can do, as they can be. That equilibrium, that's going to be a dynamic equilibrium. There'll be movement in both directions, but mostly it'll be in this direction in the short term. It'll happen through regular osmosis, and it'll happen through this facilitated diffusion or facilitated osmosis through this aquaporin. All right, let's go on and look at the next. What do you expect to happen over time in Brittany's cells? Well, you'd expect the cells to swell up and the concentration of salt to decrease. Water will move from outside the cell to inside the cell. So this is not the case, right? Because it says from inside to outside. That won't happen. Water move from outside to inside only. The only part bothers me. Water will move in both directions, but more water will move inside. This is the most correct so far. Water will move in both directions, but water will move outside. That's not correct. And water will not move, and that's not correct. So the best answer here is C. Whenever you get a set of multiple choice questions and you see there's two of them that are close, all you got to do is highlight the one question, the one word. In this case, it was the word only that put a question to you, made you question that particular answer choice. Just make sure it's there and write your notes down quickly, as I just did, and then come back and choose the best of the two answers and then move on. So yeah, water, we expect to move in both directions, inside mostly. Brittany was treated for hypoatremia, which means low solute concentration. The treatment included giving her an IV of fluids with normal or slightly higher sodium concentrations to correct the salt imbalance in her tissues. So they gave her salt water in her blood. Specific concentrations of salt to allow that to rebalance that salt concentration, to stop the water from leaving her blood and going into her cells. The problem associated with acute or sudden hypoatremia, and would I expect you to know what hypoatremia is? No, but I expect you to kind of look it up. So the sudden or acute hypoatremia or water intoxication is swelling of tissues due to osmotic uptake of water by cells. Fortunately, because she received treatment, they were able to reverse the swelling effects before her brainstem was damaged. So if they would not have done this, her cells of her brain would have been irrevocably damaged. They could have lysed. And if the brainstem specifically if that would have happened at the brainstem specifically, then her heart would have stopped. And that would have been the end of her life. Hyperturia can be very serious because of the possibility of brain damage. So that's the that's the biggest. That would have ended her life. However, you could get slight brain damage in places like your memory or your cognitive function or your reaction time. You could end up having trouble walking or moving limbs, your arms, or feeling. You could have numbness for the rest of your life. There's all kinds of things that can happen with the brain. Specifically, is very sensitive because it can't repair itself the way other tissues can. But this swelling occurred not just in the brain. All this swelling occurred all over the body, in the kidneys cells, in the liver cells, in the heart cells, in the muscle cells. All this was happening all throughout all her cells of her body. Very difficult to manage this kind of systemic, meaning system-wide problem of a salt concentration imbalance. So Brittany Chambers of Colorado in 2001, Leah Betts of Great Britain in 1995, and Anna Wood of Australia in 1995 died after reportedly taking ecstasy and drinking large amounts of water. That's really sad. Fraternity hazing killed Matthew Carrington, a student in California, in 2005. In Sacramento, Jennifer Strange died of water drinking contest. Hold Your Wee, sponsored. 28-year-old female Boston marathoner died in 2002. Artist Andy Warhol died after hospital staff accidentally administered excess water after a gallbladder surgery in 1987. So the hospital killed him by giving him excess water. Wow. Likely IV fluids, but infants fed diluted formula for extended periods of time can suffer from hypoatrimeia. That's really sad that you could, just by diluting the formula, you can impact the child. Of course, the babies are more sensitive; they're smaller, and that's just really sad. I never even knew that happened. But in any case, sad. Passive diffusion, facilitated diffusion, remembering that this is how water would normally pass right through the membrane. Oxygen passes this way, no problem. This is how perhaps aquaporin would help water pass through the membrane. Active transport, remember, requires energy. Usually it will be going from low to high. So you're going to move the ions it's going to be an ion or a larger particle like glucose from low concentration to high concentration. How do you get big molecules through? If they can't even fit, if you can't make a door big enough to get into the cell, how do you get large molecules through? The answer is endocytosis. So the membrane folds. The Golgi, in the case of the Golgi apparatus, this is exocytosis, right? So exo, getting it out. So here in the Golgi apparatus, these proteins or products of the cell, could be lipids, it could be both, produced in the endoplasmic reticulum, then transported to the Golgi apparatus. They fold. It makes a vesicle, like the vesicle you saw in the synaptic, in the neurons, right? They were held the serotonin. So if this is serotonin, it would be the Golgi apparatus of the neuronal cell would make the endoplasmic reticulum would make serotonin. It would be transported to the Golgi apparatus. The Golgi apparatus would then envelop put the serotonin in an envelope of membrane, a vesicle. It would create a vesicle that would have neurotransmitters in it. And then that vesicle would fuse with the outer membrane of the cell. In that case would be an axon, and out they would go. Now, those would be for molecules that are too large. Serotonin is small enough that it could fit through a transporter, so it could use facilitated diffusion. This is exocytosis for molecules that are too large to fit through channels like that. So these are some of the references for the slideshow. I thought this was well done. I really thought it was well worth your time to go through it, to see a real life application of ecstasy and not ecstasy, of osmosis and diffusion, and the impact of a drug like ecstasy on your health, but also the fact that many of these cases, many of the things that we just take for granted, are driven by these fundamental forces that we're discussing in class.